one of the places it can be used, you can use it. Maybe you want to know, maybe you are comparing some oranges, which one is the best? And of course, we know we usually get what? Citric acid from the oranges. So you can be able to do what? To do analysis to actually determine the amount of acetic acid. We have the drugs like aspirin is usually salicylic acid. So you can be able to, if you want to know the amount of aspirin in a certain drug, you can do acid-base titration. Let's take, for instance, something like vinegar. We know vinegar usually contains acetic acid. So again, we can be able to do analysis of acetic acid in vinegar. So basically, acid-base titration, apart from what we did in the experiments, like, you know, we were just doing for the sake, you just take sodium hydroxide and add HCl. But it can find a lot of application, especially in real life, whereby we have to make decisions, right? So we need to do quantitative analysis, or sometimes we need to do qualitative analysis. So it can be used in several ways. Now, you know the procedure of doing titration. You prepare a standard, then you put it in a burette, then you measure your sample in a flask, then you titrate, and then you record the volume, and then from the volume you can do the calculation, right? Now, let's look at different, when you are doing titration, we usually have titration curves. What are these titration curves? That's what I want to teach you today. And I'll switch gears here and go to another presentation which captures that. Now, whenever you have acid-base titration, when we talk about a titration curve, take note of this. I want you to, actually I want to go, it's here. So whenever you are doing titration, you usually have a curve whereby we can have pH, and the volume of the titrant. So what is a titration curve? Is a pH graph, a graph of volume versus volume of the titrant added versus the pH against volume of the titrant. So basically, let's say, for instance, we have our burette here, and we have our flask here, and you have our pH. Let's start with, let's say this is a base. Let's start, whatever is in our burette is a base, and whatever is here, now the solution here is an acid. Let's say it's an acid. I'll write A as an acid. So what do you expect? If you insert a pH meter here, do you expect your pH to be below 7 or above 7? Anyone? You have your acid, is what you are titrating, is whatever your sample is an acid, then your standard is a base. You want to start measuring the pH. Where do you expect? Is the pH greater than 7 or less than 7? Kindly be fast. Is it less than 7 or greater than 7? The pH meter is in the solution which is acidic. Yeah, people were saying greater, less than, below 7. Actually, because it's an acid, then it will be less than 7. So basically, when you start titrating, when you add some base here, now basically what usually happens? Is that now the pH start rising, or start going to the base, because now you are reacting that acid. So the acids or proton ions are being depleted. So basically, what we usually have is something which looks like this. which is given here. Now, you are seeing here from this part here to this part here, this part to this part here, basically there's no much change of pH. Let's look at this part here, there's not much change of pH. So this part here, where there's no lot of change of pH, this part up to there, if you are taking notes, write that part is called buffer region. This part is called buffer region. I know you guys will know what is a buffer. So a buffer is a solution which resists change of pH. So basically here, this part from here where we don't have a lot of change in titration curve is called buffer region. Then when we go beyond the buffer region, any addition of any volume, we usually have a very rapid change of pH. That's why we have the steep part here. If you take the middle of that part here, we usually call it equivalence point. So what is equivalence point? Equivalence point is the point whereby the amount of titrants being added has completely neutralized the unknown or the acid, because the unknown usually put in the Erlenmeyer flask. So when the point whereby you have added enough volume of base which has reacted with the acid, that's what we call equivalence point. Now, do we stop when you're doing titration? Is that the place we usually stop? Sometimes we don't usually stop there. So I'm trying something here. I've seen. So here, so this equivalence point is where ions have reacted with proton ions. That's what we call equivalence point. But we have another point whereby now we are getting another flat region, whereby this point, we call it end point. We call that point end point. What is end point? End point, just like this one, we call it end point. The end point is where the indicator changes color. So you can, from the high school when you are doing titration, what indicated when to stop the titration is when you saw the change of the change of colors of the indicator. Basically, that is what we call endpoint. But when you are doing calculations, you assume that the amount of the base and the amount of the acid is equal, right? Or the moles of that reacted is equal to the moles which is added. So basically, when you are doing calculation, you usually use equivalence point. But when you are doing titration using indicators, what you usually face is the endpoint. And if you can look at here, this volume here, you see there's a difference. And basically, this is one of the source of the errors when you're doing titration. That we usually use equivalence point for calculation, but basically if you are using an indicator, is actually this volume you are measuring. Okay, so take note of that. One of the source of errors in titration, it's because we usually use the endpoint, and the endpoint is where the indicator changes color, as opposed to using equivalence point. It's very important to note that. So basically the shapes of titration curves looks like this, but these shapes don't look like this every other time, because for instance, let's now we say this is not the acid. Now the acid is in we have our acid. Now our acid is in the burette, and the base is what we want to know, is the unknown. So basically, when you put your pH meter, now the pH would be below, it will be above. So the titration curve will look like this now, because still the same definition. This part from here to here is buffer region. Then we have the equivalence point there, and we have the end point now here. So depending on which solution is in the burette or which solution is unknown, then it dictates the shape of the titration curve. So it's very important to note that sometimes if the acid is the one which is in the burette, is what you are titrating, or actually let's learn this. The unknown, if the unknown is the base, then this is the way your titration curve looks like. If your unknown is the acid, then you start from below. Okay, it's important. But these shapes, now the equivalence points, are they always in pH 7? Because, and actually now take note of this, because this is what now when we'll start learning about how to actually select how to select an indicator, this is what we'll be using. No, now the question is the pH or the equivalence point, is it always at pH 7? The answer is no. The equivalence point usually depends on if you are reacting strong base, strong acid, strong base, weak acid, and that's what we'll be learning. You'll see why sometimes the equivalence point is not at pH 7. Okay, now, so shape of titration curve, one, what we have said, it depends on what solution is titrated against. We have said if it's a base, it starts from the top. If it's an acid, it starts from below. Again, it depends if the acid is a monoprotic or polyprotic. What that means is, if, let's say for instance, if we have an acid which has two, because sometimes we have the reaction for the two hydrogens, let's say sulfuric acid. So what you expect a titration curve for that, it will have two equivalence points. So it will have the first one where 1H is used, then we'll have another buffer region and another. So we'll have one equivalence point for the 1H and another equivalence for the other H. So for diprotic or polyprotic acids, so for monoprotic, we have one equivalence point because we only have one H. Okay. Now, for diprotic, we'll have the first neutralization of the first H and the second neutralization. Actually, this is what is demonstrated here, the reaction which are involved. Okay, the reaction which are involved. So if it had triprotic, if it had 3 hydrogens, then you expect the first part for the first neutralization of the first H, then the second part of neutralization of the second H, and then the third part of the neutralization of the third H. So the titration curve, one, depends on what is precipitated against, if it's a base or an acid. Then the way the number of equivalence points usually depends on the number of H's which are available. If it's HCl, we know it has one H, then we'll have only one equivalence point. If it's an acid with 2 hydrogens, like sulfuric acid, then you expect it to have what? 2 equivalence points, and so forth. Okay, I hope that's clear. Shadrach, if you're not seeing the screen, kindly refresh your browser. Now, don't want to hide that. Okay, fine. Now, so I hope that is clear on the shapes. Let's start on now. This is what I was talking about. If it has different H's, so all these, if it's triprotic, diprotic, or something sort. So that's what dictates the shape, the number of equivalence points we have. That one, I think we have brought it up. Now, let's look, and I want you to pay attention here. I want you to pay attention very, very closely. Now,
which is the equivalence point? It's below 7, so it is.
Let's say we have, and if you have somewhere writing notes, kindly do that. If you have, now you are reacting a strong base, an example, sodium hydroxide is a strong base, and a strong acid. We have started with strong base, strong acid. If you have that one, right, then when you do the reaction, we know very well when you add a base, a strong base, and acid, what is the resultant? Is usually a salt. Is a salt, that is sodium chloride plus water. So a salt doesn't have pH, therefore the solution, the end solution of a strong acid, strong base is usually neutral. So when you are reacting a strong base and strong acid, like sodium hydroxide and HCl, the equivalence point is usually at 7. Take note of that. Evans Kinodia, refresh your browser. Now, so take note of that. Reaction of acid and base usually gives a salt and water, and is usually a neutral solution. Therefore, the equivalence point is at 7. Now, it depends, whatever is an, like if you are doing sodium hydroxide plus HCl, so you know very well if the titrant or if the base is what is in the flask, then you know that's why you have this shape. If the acid is the one is in the flask, that's why we have this kind of the shape, right? So we can have these two types of the shapes depending on what is being titrated against, but the pH is at 7. Take note of that. Now let's go to another titration. Let's say we are titrating. Give me an example of strong acid. Anyone, can you give me an example of a strong acid? Give me an example of strong acid. HCl is a strong acid, sulfuric acid is a strong acid. Now, can you give me, Evans, I have already replied, lower your hand. Evans, I have already told you, just refresh your browser. Now, can you give me an example of a weak base? A weak base, I've given you a good example. Ammonia is a weak base. So an example of a weak base is ammonia. Now, if you react ammonia, which is a weak base, you add, that's a base, you add an acid, then what you expect, if you react that, what you expect is ammonium. And we know the maximum H of ammonia can take is 3. If you add the fourth one, then it will have an excess of charge. So that's the end results. So when you have this end result, now, whenever you have a positive thing, is this an acid or a base? Whenever you have I want to refresh this so that I think I lost something. Now, when you have the positive part, is it an acid or a base? When you have a positive thing, is an acid, right? Now, therefore, the end solution after reacting a weak base and a strong acid, the end solution is usually acidic. So where do you expect the equivalence point to be? If the end solution, we have said, for strong base, strong acid, the end solution is neutral. And we said that then the pH of at equivalence point is 7. Now we have this reaction, but now we are getting acidic solution. So with that, where do you expect it to be? Is it supposed to be below 7 or above 7? Good, Patrick has said below 7, 26,908, below 7. For sure, it's below 7, right? Because the end solution is acidic. So therefore, take note of that when you are reacting a strong acid and a weak base, then the end solution is usually acidic, and therefore equivalence point is usually below 7. Take note of that. Now, I think now you understand. Now, if you do, let's start with, now, what if you do a weak acid this time around? And weak acid, some of the examples of a weak acid is acetic acid, methanoic acid. Most of the organic acids, they are weak acids. Okay? So if you react a weak acid now and a strong base, like sodium hydroxide, the resultant is we usually have, like this one, if you react, the resultant will have acetate ions, which has SH3 COO negative. Or in general, if you take a weak acid and a strong base, you usually get a solution. Take note of that general one time circled. Want to delete that and circle it very well so that you can follow. So the end solution here, the general formula is you take an acid plus a strong base, a weak acid plus a strong base, usually get a negative resultant solution, which this now is what? Is basic. And when it's basic now, where do you expect your equivalence point to be? Above 7. Okay? Yes, Patrick have said above 7, and I can see Federius have said above 7, so I can tell people are following, right? So when you react weak acid, strong base, then pH is greater than 7 because the end solution is basic. Now with that information, now we can actually, now the last one, when you do weak base and weak acid, we have already said strong base, strong acid. Now weak base and strong base, the pH is usually around 7, but you are seeing now it has a funny shape. The equivalence point is not usually very well elaborated. Okay? And that's why most of the time you find that we don't usually do reaction for the weak base and the weak acids because of the type of, you see it has a very long buffer region, and then when you have, it changes a little bit. But what I want you to take note is that whatever, if you take a weak acid like acetic acid plus a weak base like ammonia, you get a neutral solution. Okay? Because here there is negative, here there is positive. Ammonium, is positive, and here there is negative, so they cancel out to become neutral. Okay? So therefore, the equivalence point is 7. So I hope you are taking note of that. That strong acid, strong base, equivalence point 7. Weak acid, weak base, strong acid, below 7. Weak acid, strong base, above 7. Okay? And then weak acid, it's at 7. So let's see what we can do with that information. Now, let's talk about how do we choose an indicator. I know in high school, sometimes you are just given some experiment and the technician prescribed an indicator for you. But this time around, you will be the people, you'll be the teachers. So you expect to guide your students. How will you guide your students? So let's start with, say, defining what is an indicator. An indicator is actually a substance which is usually used to determine the endpoint. You remember how we define the endpoint is where the indicator changes color. And it's usually a weak acid, an organic weak acid, which at certain pH it has one color, and then when pH changes, it changes color. So basically that's why we have, let's say for instance, just for instance here, if we have methyl orange, we know that it changes from pink to yellow. We have methyl red, it changes red to yellow. Litmus, red to blue, we know that, yellow to red. Now, Why we usually use different indicators is because at the pHs they changes. For instance, methyl orange can change, it changes the color between the pH of 3.2 to 4.5. So with the knowledge, remember we had the knowledge that different, when you react different acids, the equivalence point is usually differently. So actually that's what dictates how we choose the indicator. For instance, let's look at methyl orange. It can only change its color between 3.2 to 4.5. So if you are doing, can you tell me now, looking at this range, and you are doing an experiment, if you have to choose methyl orange, will you choose methyl orange when you are doing strong acid, strong base, weak acid, strong base, or strong acid, weak base? With the knowledge we had, so we have this methyl orange, and let's have a recap that strong base, strong acid, the equivalence point is at 7. Strong base, weak acid, the equivalence point is above 7. When we have weak base, strong acid, the equivalence point is below 7. And weak acid is at 7. So if you look at methyl orange, it can be used as indicator for which reaction. Somebody, Shadrach, has said strong acid and weak base. Lemayan have said strong acid, weak base, same answer. Vincent has said strong acid, weak base.
Oh.
So why strong acid, weak base? If you have not followed, let's see if these people are correct. Weak acid, strong acid, weak base. Strong acid like HCl, right? Plus weak base like ammonia. So the resultant is what? Ammonium, which has a positive. So this is acidic, and therefore equivalence point is below 7. Therefore, when it comes to
manini.
orange can be used for this reaction. This again also is below 7. Also, methyl red can be used. Okay. What about this one? The ranges go beyond 7. As much as this can be used too, because it captures something less than 7. But what about this one? We cannot use phenolphthalein or phenolphthalein because the equivalence point is above 7. Okay. I hope now it's clear. So people who have said strong acid, weak base, they are correct. Yeah. Now let's do some exercise so that one, I'll know who is in class, and two, I'll understand if you have understood. An exercise here on choice of, I will ask you a question, then I'll go back to now. If you have a piece of paper somewhere, I want you to write part A and part B somewhere else, so that I can take you back to, I know you guys, you have not come to the table. So can you write it down? Titration of hydrogen iodide and ammonia. Okay. Then titration of hydrogen iodide and sodium hydroxide. What I want you guys to do is this. You write the reaction which is involved. You know, here you will just add one H here for it to become ammonium. Here you know very well, you'll have to add, this is sodium iodide plus water. So wherever you are, now the answers I want you to post is A, if you say A below 7 or A equals to 7, A greater than 7, right? That's what I want you to write. Like, write the net ionic equation. So write somewhere in the paper. Then when I open the poll, I want you to tell me A, equivalence point, if it's above 7 or below 7 or equal to 7. B, if it's above 7, below 7 or equal to 7.
Citric acid.
That's the answer I want you to write when I open. Okay? The net ionic equation, write somewhere, wherever you have some writing place. Okay? And after that, I'll take you guys. So that's the first poll. I'm opening the first poll, which I expect you to write A is equals to 7, is below 7, or is greater than 7. And then B, you write. So it's typed answer and start the poll. So let's start with, I'll start with A. I want you to write the answer for A. So I want you to write the answer for A. A alone.
Weak base, weak and strong acid plus weak base.
And the answer should read below 7, equal to 7, or less than 7. That's what I do. I don't want you to say approximately 7. There are only 3 choices: above 7, below 7, equal to 7.
Kera koni na kerathi. Gakemu gakorwo na cama we. Gakemu ga university taka secondary man.
So we have 105 users. I have answers for 70 users currently.
Ikaga uguo analyzing. Kirathi gake niguo ekaga. Eni, nona warega kuiuria. Kirathi kiu ndurariku.
And kindly, because we are right now it's 11:53. I want you to be done within, that's something less than a minute. So by 54 should be done. That's when I'll close the polls. So I'm seeing people saying below 7 for the answers I've gotten 80 students from 80 students. 33% have said below 7, 11% are doing. So keep going. I have 85, 20 students are yet to answer. Kindly don't answer it in the public chat. Answer it in the polls. So, and basically, I'll go ahead and close the polls. And of course, those people who have said it's below 7, they are correct, because if you take hydrogen iodide plus ammonia, this H will be taken that, so actually it's iodide plus ammonium. So the solution is acidic, and since it's acidic, then the equivalence point will be below 7. And I'm seeing 72%, actually not 72% because of the wording. Then actually I think almost 90%, only 3 people said below 7. So those 3 people, I hope you are able to see why we are saying is below 7. The other ones, it's only 3 people who said Not below 7, sorry.
No, na wili na
6 people said is equal to 7. You are saying y is not equal to 7. Then one person saying is above 7. You have seen y is not above 7, is below 7. So I hope that is clear. Now, after saying that, now we have agreed that the answer is below 7. Now let's go to the choice of, and we have to be quick here. Then let's go to the choice of indicator. The choice of indicator. Now, we have said it's below 7. So what I want you guys to type from this, now choose for me. Let's
Below 7.
let us not do this. Let's go to question B, because that one I think question B will be a nice one to see if you have understood. Let me start the polls for 7, part B. So part B,
This one can supposed to become sodium
part B,
iodide plus water. That is
part B, we are titrating hydrogen iodide and sodium hydroxide. The answer for this is you are getting sodium iodide, which is a salt, and water. So can you tell me if the equivalence point the same way, if it's equal to 7?
equal to 7.
Part B answer equal to 7, greater than 7,
Less than 7.
or below 7. For part B, we are getting a salt plus water.
Salt plus water is 7. 37.
Seeing there is 4 people who have said above 7, equal to 7. We have majority saying is equal to 7.
Equal to 7.
Greater.
Remember, a salt is usually neutral, water is neutral. So is it equal to 7, above 7, or less than 7?
Equal to 7.
Because we have only 2 minutes, I'll stop there. Because we are making a salt and water, that's neutral. Therefore, is equal to 7. So those people who are saying is equal to 7, they are right. Those people, like I'm seeing 6 people, 12 people saying it's above 7. You have seen why it's not above 7, because you are making a neutral solution. Whenever you are making a salt, like sodium iodide plus water, is usually equal to 7. Now, having known that is equal to 7, now what I want quickly, because I'm seeing we have less than 2 minutes, before we are thrown out of the class. Now, can you tell me, now I'll stop that poll, and I'll start another poll.
Below 7.
Now, tell me part B, which indicator can be used? We have said is equal to 7. Can you tell me the indicator which can be used? So your answer should be either methyl orange, methyl red, litmus, and so forth. Okay? I've started the poll. We have less than a minute. From that table, we have said is equal to 7. People have said litmus paper, which ranges from 4.5 up to 7.5. We can see 7 is within that range. So, any other?
Phenolate.
Yes, somebody has said litmus paper. And actually, I want you to list from this list. Don't list one. If there are 2 or 3 indicators which can be used, you can list. Like I'm seeing somebody has said litmus paper and phenol red. Or are we still in class? Because I think we are yet to be thrown out, so we are good. So how you choose the indicator, like this one cannot be used. Why? The 7 is not within this range.
Yes.
So this one can only be used to when the solution is what? Is
acidic
solution. And it's when you do what? You do a weak base and strong acid. For methyl red, 7 is not captured, so we cannot use methyl red. Why? The equivalence point is beyond 6.5. Litmus paper, we can be able to use it, okay, because you are seeing here 7 is around there. So this one can be used for strong base, strong acid. Phenol red can be used because still 7 is around there. This one cannot be used because the 7 is below, it's not captured within the range. So basically, that's how we usually choose. So if you know, if let's say for instance, you are doing an experiment and you look at what's called, the acid or base you are using. So you categorize it. If it's a strong acid, strong base, then actually you can make a decision on what thing to use. Therefore, Dennis Mulwa, can you type what anyway, so I think it's very clear how we choose indicators. Unless you have a question, it's good, you know, it's connection problem, then you can so can you still hear me? I wanted to know, can you still hear me? Okay, then it's a good thing we are yet to be thrown out of the class. So I was getting afraid that if the class go beyond 12, we'll be thrown out of the class. So we are good to go. So I don't need to rush. So now let's do the last one. The last one, so that we can see if people understood. Let's go to part C. And we see if we can be able to actually determine these are strong acids, strong. Now the answer for this, sodium hydroxide plus hydrogen fluoride. So we have sodium fluoride and sodium hydroxide. Actually, basically the answer for this will have sodium fluoride, which is a salt, plus water.
But sodium fluoride is a base.
But fluoride, I love you guys to know, the ionic will be, let me write for you guys so that you make the right decision on this. I know it's a tough one. No, it's not a tough one. This one is a salt. It's a salt. Actually, this one, basically the ionic equation for it is that, because we don't usually include, so it's just the end solution is water. Let's make, don't answer that. Let's do this. Let me have at C 00 plus acetic acid plus sodium hydroxide. I want you to tell me. I want to delete this one so that I don't confuse you.
And these are neutral.
So I want us to determine the what's called the indicator for this reaction. This is a weak acid and a strong base. What we usually get after doing this, we get acetate ions, which are negative, CH3, the O negative, plus water.
So this is a...
So we have acidic solution. Take note of that. Not acidic, sorry, basic solution. So have you taken note of that? Because this is the question I want you guys to actually answer. we have a basic solution. So the equivalence point is what? Is above 7. The equivalence point is above 7. So I want us to choose an indicator for this reaction. Let's go to the table. I hope you have taken note of that. Let's find an indicator for that reaction. So you have the table there. I'll start a poll. So what you are supposed to write on that poll? Can you hear me?
The grass has been cut.
Can you be able to hear me?
So
what I want you to write on that poll, just
above 7.
want to start a poll. Just a minute. So start a poll, and what I want you to write for me is that we have seen that that reaction is giving acidic, not acidic, basic, which equivalence point is greater than 7. So from this table, can you list all the indicators which can be used for that reaction? So give indicators.
Arakisha.
Indicators for that reaction is a type 1 and start a poll. So can you be able to list all the indicators which can be used for a reaction which is equivalence point is greater than 7?
Twaruta kĩrathi. Tũtirutĩtwo. Ndona ndĩ kĩrathi we. Aca. Ithe tũrathoma nginya cia next week.
I'm seeing 55 students out of 90 students who are now, I think 10 people left us.
Kuboeka.
Yoko. Why?
So we are seeing, so basically, so that now I know people are trying. I'm seeing 70 students have done that. So when you are doing the answer, it's be above 7. Therefore, methyl orange cannot be used because the maximum it can go is 4.5. Methyl orange, the maximum it can go is 6.5. Now litmus can be used, but you see that as much as it's below 7, you'll find that most of the time it goes beyond 7. So this one is just a little better. So yes, it can be used. Is there yes or no? Because the range, this one, the maximum is almost at 7. So litmus paper can be used, yes, but sometimes it's not the best choice because equivalence point might be, you see this one is very close to 7. So this one is a good one for, especially for as strong as a strong base. But this one is a yes or no. This one, it's well go beyond 7, so it's a good one. This one is the best because you can see it goes above 7. So therefore, people who have said litmus, phenol red, or phenolphthalein, then those are indicators we can use. And I'm seeing so many people have the correct answer. Therefore, comfortably, I can say that that class is well delivered. Okay? Now, Now, what else do we do? Because at the end of the day, volumetric analysis, what you're interested in is in calculations, because at the end of the day, it's analytical chemistry, and what we want is to be able to have some calculations. This one, I cannot teach much because the choice of indicators we have talked about. Now, how do we go by when we are doing calculations using using volumetric analysis? This one you have really studied for, I think, was it first year or second year, like form 1 or form 2, that the first thing you're supposed to write a balanced equation for the reaction. Then you are supposed to balance it to know the mole ratios. Then from there, now from the mole ratio and the volume you have used, then you calculate the moles. Then after calculating the moles, after calculating the moles, then you can determine, after calculating the moles, then you can determine actually the concentration of your unknown. So this is a procedure which you have done from form 2, so I don't need to go by. So, and what I've done to help you out, to remind yourself, for instance, let's say we have 25 centimeter of, not centimeters cubed, of potassium hydroxide, that is a base. Then you require around 30 centimeter of that solution of the base of an acid to completely neutralize. So what basically this question is, after titration, you used 30 centimeters. So you want to calculate the molarity of your solution, right? The molarity of your solution. That is, so basically you are starting with 0.12 molar of the base, and you take what? 25 centimeter of that base. Okay, then you react it. So we have said the process is, first of all, you write the equation and you have to balance that equation. Then after balancing, that one is something you have done over and over in high school, so that this is not a problem, balancing an equation. Now from there, we know after titration we used 30 centimeter cubed. So what we do, the first thing is you find the moles, because we know the molarity of, let's go here. We know the first thing we need to know how many moles we have added or we took, right? So we know very well when we say 0.12 molar, we mean 0.12 molar in 1,000 centimeter cubed. We took how much? 25 centimeters. So we know very well how much of the moles did we have is 0.03 moles. So if you want to calculate the molarity of your base, then from the equation, we have seen that mole ratio of the acid, of the base and the acid is 2:1. So for every 2 moles of this, you have 1 mole of this, and therefore if we had 0.3 moles of this, then how much of this do we have? So that one, I don't like teaching somebody how to calculate this. Calculate it the way you are taught by your chemistry teacher. So I don't like corrupting your mind here. Calculate it, so long as you know you are calculating moles. Then after that, now we know how much of the moles of the base we used, and therefore now for the moles, we know these moles. Now you have to put it in what? In 1,000 ml. So this is 0.15 moles in 30 centimeter cubed, right? What about in 1,000, which makes liter? So when you do that, you find that the molarity of the base was 0.015. Here, there's not much to teach. Is you doing the exercise. So you already know how we can use volumetric analysis. You have done before. So what I have done is giving you several questions, and I've given you those questions with worked solution. So I urge you, go and read the question, try to do your way, the way your chemistry teacher taught you, and see if you can come up with the answer I've given.
Okay.
I've given several exercises. There are several exercises, assignment. Those assignments, those which I have not given the working, I've given an answer. Okay? So you can be able in your group sessions or with your friend who is your academic partner, you can always try this question.
Nathiĩ thukuru
You calculate and see if you are getting that
Alright.
answer. So
kũgĩra wini
I think I've put enough questions for that.
Nĩgũka.
Then
Nĩgũka.
when I send these notes, I want you to,
sawa mũnene
so these are the exercises I want you to do for acid-base titration. So I want you to read for acid-base titration. I want you to go up to this part. Okay, that's therefore next week we'll start doing oxidation reduction reactions, and we'll just give, for now I want you, when you'll be reading the notes, the end part of that, the relevancy of those notes will end up here. Okay, the rest, if you want to continue for future reference, you can do, but we won't be learning this for now. For now, we won't learn on that, on balancing, oxidation reduction. What I wanted you guys to do or to understand is acid base, because mostly you'll be dealing with acid base titration. But for your references, you can still leave those notes there. Sawa. So next week, I really wanted, I'm seeing here, now we have the complexometric titration, which you have done today. And that one we learn next week. Next week, I'll be having a research tour somewhere. So I would be able to, I would be in the university. I really wanted us to have this week class physical, and then next week we'll have online, but because of what happened yesterday, I was unable. So I'm left with no choice. The next lesson would involve a lot of calculation, so I'm comfortable teaching it online. We'll just go through the types of